For the last month, Sarah, a data analyst at North Star Retail, has been predicting customer churn. She was using supervised learning, feeding algorithms a giant spreadsheet where every single row was tied to confirmed outcomes. The model learned by matching customer habits to these pre-existing labels. Today, her boss Marcus dropped a new assignment on her desk. By Friday, she needs to group their entire active customer base into distinct behavioral segments and generate a watch list of anyone acting out of the ordinary. The complication is that there are no historical labels to guide the model this time. She has no ground truth to grade against, meaning the algorithms have zero context for what a normal or weird customer looks like in this specific dataset. This requires unsupervised learning. Instead of teaching a model to predict a specific target, we are asking the math to independently discover hidden structures and natural relationships buried in the raw data. Removing the labels forces a transition in the data science process. You are no longer grading a test. You are stepping into a dark room and surveying an entirely uncharted territory. North Star's dataset tracks 17 different metrics, things like tenure, total purchases, and return ratios. Human brains cannot visualize a 17-dimensional space, so Sarah's first step is to compress the data. This animated chart shows what happens if we don't prepare the numbers first. Total annual spend, measured in the thousands, mathematically drowns out a crucial metric like return rate, which maxes out at 1.0. To prevent the biggest numbers from deafening the algorithm, Sarah scales the data, putting every metric on an equal footing. With the scales balanced, she runs principal component analysis, or PCA. This mathematical compressor takes that unreadable 17-dimensional cloud of data and flattens it down into a crisp 2-dimensional map. PCA merges related metrics that naturally move together, like tenure, frequency, and spend, into single variance-rich axes. This allows Sarah to preserve the signal of 3 columns in a single axis she can confidently label engagement. What started as a sprawling, incomprehensible spreadsheet is now a clean scatterplot sitting on her monitor, capturing the entire North Star customer base in one glance. Dimensionality reduction is the required first step because raw, uncompressed population data is too dense for strategic decision-making. You have to build the lens before you can study the landscape. Now that Sarah has a readable map, she needs to draw borders on it, grouping these dots into actual market segments. This diagram shows k-means clustering in action. The algorithm calculates the distance between every single customer and pulls them into dense, natural spheres of similar behavior. But k-means clustering cannot identify how many groups actually exist in the real world. It relies entirely on human parameters, meaning it will force the data into 2, 4, or 7 distinct groups, depending on what you ask for. To find the right number, Sarah runs mathematical checks like elbow plots and silhouette scores, but real data often yields smooth curves instead of sharp answers. Ultimately, she sets the cluster count to 4 because the marketing team has the bandwidth to run exactly 4 campaigns. The algorithm's output is just a list of integers, 0, 1, 2, and 3. Sarah closely examines the underlying data for each group, observes high spend and low returns in cluster 0, and assigns them a descriptive profile like loyal premium. The math draws the territorial lines with mathematical precision, but it takes a human being to look at the averages and actually name the segments. With the marketing segments locked, Sarah turns to the final piece of the Friday deadline, finding the customers who don't fit in at all. She deploys Isolation Forest, an anomaly detection algorithm designed to sweep the sparse outer edges of the dataset. It ignores the dense centers and flags the 5% of dots that exist on the fringes of every group. If we expand one of these flagged dots, we see why it was caught. An anomaly is rarely a single extreme value. Instead, the model spots highly contradictory combinations, like a customer with 70 months of tenure, 0 recent purchases, and a sudden spike in support tickets. Sarah exports this list, but she doesn't use it to automatically ban accounts. She hands it to the customer success team so they can investigate the complaints and try to save the relationships. Anomaly detection works as an automated spotlight. It sifts through the noise of hundreds of thousands of routine transactions so that human judgment can step in exactly where it is needed most. By Friday afternoon, Sarah presents her findings. A raw, unlabeled spreadsheet has become a compressed visual map, a targeted marketing breakdown, and a specific risk management watch list. She followed a sequence: map the chaos by compressing dimensions, draw behavioral borders to find the tribes, and sweep the outer edges to catch anomalies. Navigating data without predefined labels isn't about guessing the future. It is about building a mathematical lens that allows you to finally see the present clearly.